Hello students, I would like to welcome you to the lecture Integrity of Materials and Structures, and we will talk today about the first exercise, number 1, and the title is Fractured Handlebar of a Bicycle. Now we start with here, we see here a drawing, a sketch of the bicycle, and I can tell you the history of the bike. It was already 6 to 7 years old, running, and it was told that it was normal biking. Now we all the time first have to think about what kind of mechanical loading is on this kind of device. You all know this is a handlebar of a bicycle. What do you think? Carefully. Of course, when we are going and biking, there is different loads on it. And since they are different, changing load, that means we have a fatigue loading. And bending, you can imagine when you go, for instance, up or down with a bicycle, then you put here on this handlebar in different directions loading. And there one of the loading directions is shown here. So we keep in mind on this construction on the handlebar is a bending fatigue. And what do we also do sometimes when we are biking? We maybe crash somewhere or go up and down, and then we have a so-called shock loading, additionally impact. Now here you see the construction and the materials used, and the construction is a bit special because we do have here the handlebar itself. It's an aluminum alloy, round aluminum alloy, and here, whereas it is attached to this kind of construction, which leads then to the bicycle, we have here to ensure here that it is more tight an steel inlet. So this makes here the construction more reinforced. And when we look here very carefully, we see again the aluminium tube and inside a steel inlet. And now I tell you something. This handlebar was fracturing during biking. So the one who was biking fell down and was heavily injured, and the fracture occurred in this plane here. Look carefully in this plane. What do we already realize? It's obviously in the transition zone between the steel inlet, where it is finishing, and here the aluminium tube. We already start to think what kind of influences can be on this kind of fracture. It will be very interesting to find out later on the real reason. But one influence you may think already, what do we know about two different materials in contact? There is first an aluminium tube and inside a steel inlet. Two different materials. What does it mean? It's like a battery. And when we do have a battery, then there is electric current flowing, and that means when we additionally assume that there is also humidity there, it's all the time humidity there, and it's trapped here, that means that there is corrosion taking place. That is one part. Another part, which we already see also here, of course there is a jump in the stress from here to here. Here is a much bigger diameter due to the construction, and here is less diameter. So a jump in the stress, it's an additional factor we have to keep in mind. What we also have to keep very much in mind, we come back to the end with this, the wall thickness of this aluminium tube, and I have here an example of this which you see here. It's a similar design, it's not really from this case, but it's a similar design, and you see here this aluminium tube, and the thickness here in this case is 1.5 millimeter. Please keep this in mind. We come back to this. Okay, now we have a look. Look, this is another example, not really that one, without inlet. Again, you see here the jump in the stress. Here is lower stress, and here is higher stress. in this region the fracture occurred. And you can again imagine when this occurs during bicycling, it can lead to a very crazy accident. Now we have a look directly on the fracture surface of these handlebar of the bicycle. What do we see here? We see, oh, by the way, I have to tell you, this scale is wrong, because you remember the thickness is here 1.5 millimeter of this aluminium tube. You see also, so you see here the aluminium tube, and you see inside the steel inlet. What can we read? And the question is anyway, what kind of type of fracture do we have here? What can we read from this image? You see this half elliptical zone in the outer part in this aluminium tube. And since we were talking about that we have banding fatigue loading, so most probably because of the change in load, it's fatigue there. And we have already here a very, very clear sign for fatigue. This is this half elliptical zone, which we see here. Maybe you remember what's the name of that line. That line is called, that is clearly a so-called beach mark. And what do we remember? In the middle of that half elliptical zone, most probably, we will find out later, there is a crack initiation zone. There is a crack initiation zone. That's very interesting that the crack initiation zone is here inside of the tube, because what do we know about the highest loading on this component? It's normally outside of the tube, but here it's inside. So that tells us that there is something special, something very wrong probably, and which has a very bad influence on that component, leading to an early stage of crack initiation. When we also watch now what's happening with this crack, which is first passing here, propagating, then approaching the outer surface, and then the crack obviously turned the direction in both sides and propagating, shown here by the arrows, in both directions. And now you imagine what is the last part here. This you also already know. This is our overload fracture. Of course, by the time there is less material available for taking over the stress, and then the stress gets so high due to the fact that there is less material available, and secondly due to the fact that there is in front a higher stress when the crack propagates. So that means here is an overload fracture. But what we already realize, the amount of overload fracture is relatively small. That means in principle, from the design point of view, the stress on this component was not that high. That shows us again that there should be something very strange going on, and this we will investigate very carefully. So we already keep in mind this is a fatigue crack, and of course we will later on watch more carefully at higher magnification on this spot and also on this propagation part. Good. Now we already watch at a bit higher magnification. You remember this is our half elliptical zone of our crack initiation. That is the inside of our tube. We watch here inside in that tube, and we realize here on this inner surface here there is again our crack initiation site. And secondly, what we realize is that in this area here inside there is these black spots, and these black spots, they clearly stand for corrosion products, and it's exactly at the contact area between the aluminium tube and the steel inlet. Of course, we have to imagine the steel inlet is now here removed, that we nicely can watch on this. Now we watch here at this area at a higher magnification, now inside in the scanning electron microscope. And what do we see there? At a higher magnification, look, this is 4 micrometers. Nearby the crack initiation site, the surface here is quite rough, really rough. When you imagine normally when you have an aluminium tube like this, the surface is like nice shiny, and here it's quite rough. So that already tells us there was most probably, we come back to this later, a sort of movement between two materials. We will see why this is coming from. This is important to keep this in mind. Okay, now we are coming back again to the fracture surface itself. We more closely watch now, because we still want to find out if it's really fatigue, crack, and again that is that beach mark which we already saw before. And now that's not so easy to see. There is also very nice to see some smaller beach marks here. And when then the crack turned the direction and propagated here, then there is even here, of course this is very sophisticated, you see here a beach mark, and you see here a beach mark, and here a beach mark. Of course, that's reality. If you make any fatigue tests in the laboratory, then it's mostly quite clear and obvious. And here, this is reality. You have to keep in mind. But finally, you can see this, these beach marks. Nice to see. Okay, now we go on this fracture surface. And we see here, in this area, when the crack propagates, now in the scanning electron microscope, see again here the scale at higher magnification. We are watching carefully here on the fracture surface, and now when you watch very carefully, you may see some parallel lines in this fracture surface. And I think you see them here. Look, there is a line, there is a line, there is a line, and. And this tells us clearly that the crack propagation was in this direction. Why do we have these striations perpendicular to the crack propagation? It is a fatigue crack, and whenever there is high stress, then the crack is pushed forward. It has in front of the crack tip a plastic deformation, and the crack is pushed forward. Then the stress goes down, and then the crack rests for a few seconds, and then the stress goes up again and is pushed forward. So each line which we see here shows us that there was a stress which was correlating, which was going up and down. So this is called striations, in German Ermüdungsstreifen. And by the way, the other ones which we were talking before, that ones is in German Rastlinien. I think it's even better Rastlinien, because it's a resting line when the crack does not propagate. That's the point. Beach marks is the English explanation. Good, let's go on. Now we are doing the following. We want to watch inside in the material to see what's happening exactly here in this area where the crack initiated. What are we doing there? We cut very, very carefully here inside, perpendicular, and take this material, embed it, and make a metallographic specimen. And this metallographic specimen is shown here. And what do we see there? This is an aluminium alloy. There is some precipitates of the aluminium, and then there is some very nice black particles, a network of black particles, and I can tell you these black particles you can analyze. It's aluminium oxide. That's very interesting. Fine network of cracks filled with aluminium oxide particles. Now you will ask yourself, where are these aluminium oxide particles are coming from, and why are they here embedded in the aluminium? Now what do we know about aluminium? When you think here of the surface of this, you have to ask yourself, is this pure aluminium, or is there something else on the surface? Of course, there is aluminium oxide on the surface, because it's a self-protection process, and we know when we scratch this aluminium handlebar, maybe I can make here already a scratch, after a few minutes it's self-healing. The aluminium is from down coming, and from outside, of course, you have all the time oxygen available, and it immediately restores the original aluminium oxide layer. But now we have to start to think why these aluminium oxide particles are produced here. And now we are coming back. You remember, or you may remember, that we were talking about this area at higher magnification in the scanning electron microscope, and you remember this scratching of the surface. So for some reason there was a movement, and of course the counterpart, remember, is a steel inlet, and these two materials obviously moved a little bit to each other, made a movement. The mechanism for this is called fretting. You have to ask yourself later on why this movement could take place. However, due to that movement, it's clear all the time of this aluminium oxide layer, which is here, it was destroyed. And by the time hard aluminium oxide, you know, it's like a grinding material, it's ceramic material, it's extremely hard, and of course it will be embedded here in this pure aluminium inside. And this is the start of a crack. That's the start of the crack. So we have here the key of our failure already. Because it's so crazy here behind, you can imagine the aluminium oxide is embedded. Here the coating, the self-protecting coating is destroyed, but it has a self-healing process. So it's again producing aluminium oxide, self-healing, then again the scratching, and again this. And of course, this takes time, but as you have seen, the fracture of this handlebar took place after about 6 to 7 years. So it's a matter of time. Of course, you have first the crack initiation part, and then when the crack is initiated, it propagates around. Maybe it takes also another few weeks or a few months. We don't know exactly, but that's the mechanism behind. Okay, now we can already conclude here, but it's not the main conclusion. We have seen fretting corrosion, damage of the protective aluminium oxide layer due to micrometer movements. This we have seen here in this area. And then it's embedded here. And the aluminium oxide particles, they are extremely hard. They act as abrasive, and this abrasive is embedded here and is then the start for the crack. Now, what is now really the main failure mechanism? And now we have to go back to the original design. What do we know? There is an aluminium tube, and inside is the steel inlet. And now there is something very important. You have to think of the different mechanical properties of the two materials. And there is one parameter which is very much different between the two materials. Think when you make a stress-strain curve with these two materials, what do we know about the Young's modulus? Think carefully. The Young's modulus of steel is in the range of 210 gigapascal, and the Young's modulus of aluminium, maybe you remember, is 70 gigapascal. So they have quite a different mechanical behavior, and from this we also will learn how to improve. And this, what I told you now, this different mechanical behavior is just shown now in this diagram. Look, now there is a stress, there is no loading, and there is a strain. Now, as I told you, we have the stress-strain curve. When the stress increases, the strain increases. We are still here in the elastic region, so it doesn't matter, in the elastic region. So that is correlates to 210 gigapascal, the Young's modulus, and that's to 70 gigapascal. So we have a different slope. So we imagine now, and I remember, that was a point of the design, which is shown here, that these two, the aluminum alloy and the steel inlet, they are fixed by this screw, tied together. But anyway, when you put a loading on this, let me say in that, doing bicycling, the stress is in this level, that means there is a difference in deformation. Strain is deformation. And this difference in deformation we clearly have seen in this movement of the materials scratching the aluminum alloy and destroying the aluminum oxide layer. That's very important. That's a main mechanism. The other mechanism that there is maybe also here some corrosion, it's additionally we have seen, but that's a main point. Now the question is coming, how can we improve that this kind of failure doesn't happen anymore? And this is also our experience, and I can tell you, without any change of the design will be the same, and also these two materials will be the same. Now, think carefully. What can we do? We can just lower the stress here, then we have here less delta strain, and there is obviously a lower limit. Now the question is, how do we lower the stress? Very easily. We just increase a little bit the diameter of that aluminum tube. And when we increase the diameter, then it's clear we have a lower stress in this component, and this is shown here. And obviously there is a lower limit for this difference in deformation, that this mechanism cannot work anymore. And I told you from the beginning that we had here, and I told you to keep in mind, this aluminum tube here outside had, for this handlebar which crashed, which failed, 1.5 millimeter diameter, and we never had any cases or failures with aluminum tubes with a diameter of 2 millimeter. So there is obviously a lower limit for that. So that is the increase. So we can now finally conclude the main mechanism, failure of the handlebar due to fretting corrosion. Of course, there is an additional influence of corrosion, which we nicely see here with these black spots. It's additionally. It's clearly an unfavorable construction. There is a large difference of the Young's moduli of aluminum and steel. And this makes then these micrometer movements destroying the aluminum oxide layer. And finally, there's obviously a too small wall thickness of the aluminium tube, 1.5 millimeter. If we go to higher ones, we never had any failures like that. And an additional effect, of course, it's not all the time, not only one influence, there's an additional one. We have here crevice corrosion in this area, again here. So there, humidity, you do not need water, you just need humid air, and the humid air is here available more or less, and then it's all the time humid here, and also the humidity cannot evaporate. It's all the time here, so it's all the time wet here. It's like an additional corrosion effect, crevice corrosion. But again, to conclude, the main point was the fretting effect, fretting due to micrometer movement between these two materials. Okay, so that was now very shortly that introduction, the first lecture, fracture handlebar for bicycle. If you have any questions, you may write to me an email, or you directly can contact me by telephone. So thank you very much and enjoy the day.